Welcome everyone from my side as well. As Ahmed said, Martin will help with any questions that come in during the course of the webinar. So if you have any questions, please type in your questions and Martin will try to provide the answers. If there are any more questions left, we will definitely try to take those questions towards the end of the webinar. Now, coming to the outline of today's webinar, we will start by looking into the evolution of wireless technologies, followed by the coexistence and interference issues between these technologies. Altair's wireless coverage and network analysis software, WinProp, is part of this solution to this interference issue. So we will learn about WinProp and its capabilities with the live demonstrations. Then we will look into the coexistence case study, which explains the interference issue between Bluetooth and Wi-Fi networks inside a residential building. And finally, we'll go through different resources provided by Altair to help students. This will be in the form of either free software or some e-learning modules and so on. But before going into the evolution of different wireless technologies, let's try to list some of the common technologies we use regularly. Bluetooth is definitely one of the most commonly used technology. We use it to connect to different devices like TVs, phones, speakers, and so on. Wi-Fi is another technology without which we may not be able to perform majority of our work-related tasks, including this webinar that we are doing online. And it became even more essential since COVID due to the remote work culture. Next is 5G or even LTE. I don't think there is anyone amongst us who doesn't use a phone which rely on these 5G and LTE technologies. Another technology is Zigbee, which is predominantly used in smart home applications like thermostats, smart lights, security systems, and so on. If we recall the evolution of wireless technologies, we date back to early 80s, where analog services were first started. The primary focus at that time was to make voice calls or send text messages. Come the 90s, the technology transitioned from analog to digital, which improved the quality and enabled worldwide connectivity. A decade later, we have technologies like CDMA, UMTS, and Edge that enabled users to access the internet using mobile devices, apart from making voice calls and sending text messages. By 2010, a few years into the arrival of a smartphone, the demand for data increased exponentially, and the 4G technologies like LTE and LTE Advanced are developed to meet those demands. The demand for data is only increasing each day, and new technologies like 5G came into existence to keep up with the demand. 5G deployments, which began in early 2019s, continued to expand since 2020s. The next generation of wireless technology, 6G, is aiming beyond 5G with a focus on higher frequencies, wider bandwidths, and a greater integration of artificial intelligence and machine learning. Similar to the cellular technologies, the Wi-Fi and Bluetooth technologies also went through a similar evolution. The Wi-Fi speeds increased from few megabits per second to few gigs. Wi-Fi technologies also evolved from using MIMO to multi-user MIMO to the latest Wi-Fi 7 using something called multi-link operation, MLO. Similarly, the connection speeds as well as the range increased with each advancement in Bluetooth technology. The newer version of Bluetooth introduced features like direction finding for indoor positioning, LE audio for enhanced audio streaming, along with optimization in speed, range, as well as power efficiency. As we have so many technologies coexisting in the same space, the interference between these technologies is a major concern. Okay? If we take, for example, Bluetooth and Wi-Fi, the problem may be a bit more severe as they both operate within the same 2.4 gigahertz of frequency band. So this interference issue affects the performance of a device, and in turn, it reduces the perceived quality of that device that we are using. And because this interference issue is directly affecting the perceived quality of a product, it is extremely important to identify these issues in the early design stages to avoid costly rework. And this is where Altair's simulation solution can help to identify the problem and iteratively test various fixes. And simulations are also attractive as they offer a cheaper solution compared to physical tests at every stage and physical rework. Simulation solution from Altair to this coexistence and interference issue can be summarized into design and in situ analysis of antennas inside the electronic devices, then the wireless coverage and radio channel modeling and interference analysis of these multiple technologies. These analyses can be performed in various scenarios like indoor, urban, underground tunnels, and so on. And finally, deployment and optimization of these wireless networks based on coverage and capacity. Let me try to elaborate a bit more on the Altair solution that I just talked about. The first part of the solution focuses on the antenna design and in situ antenna analysis combined with powerful optimization routines. All of this is part of the high frequency 3D electromagnetic simulation software from Altair, which is FECO. In fact, as part of this IEEE webinar series, we already delivered 2 webinars on the topic of antenna design using FECO. One in December of last year and the other in February of this year. And both those recordings are available on YouTube. If any of you did not attend those webinars, I encourage you to watch those recordings. Coming to the second part of Altair solution, it involves wireless coverage and network analysis using fast and accurate propagation models in WinProp. WinProp is another software within the high frequency EM suite from Altair. Some of the primary applications of WinProp include wireless coverage and radio channel modeling, deployment and optimization of radio networks, virtual drivers for ADAS applications, as well as antenna performance analysis, and coexistence of wireless networks and electromagnetic exposure as well. All these applications are the wireless network simulations that I just mentioned. They can be performed in different environments or scenarios like indoor, urban, rural, or underground tunnels and stadiums, and so on. And for the wireless network analysis, WinProp supports almost all the standardized technologies like 5G, LTE, Wi-Fi, Bluetooth, Zigbee, LoRa, CDMA, GSM, Tetra, almost everything. When it comes to wireless coverage of a transmitter or several transmitters in any scenario, it's a very straightforward analysis in WinProp. However, to characterize the radio channel and understand the network capabilities, we need the air interface models. An air interface model is nothing but it includes the specifications of the given technology, including the frequency bands, channel bandwidth, modulation schemes used, duplex separation used, MIMO scheme used, if the technology supports MIMO, and so on. And WinProp provides a huge library of these different air interface models for various standardized technologies. So if you can see the long list on the screen, you can see almost all the standardized technologies. If you're working on an emerging technology that is not yet standardized, you have the option to define the air interface manually and do the network analysis for that emerging technology. That option is also available within WinProp. When it comes to propagation, in general, a radio channel is subject to multipath propagation, as a direct path is not feasible all the time. For example, in an urban scenario with a base station transmitter above a rooftop level and the mobile station or the receiver located in the street canyon, there can be multiple rays connecting the transmitter and the receiver with the different delays and attenuations. The dominant propagation effects are the reflections at building walls, the diffraction around the corners, and the shadowing behind the buildings. The superposition of the multiple rays at the receiver will lead to either destructive or constructive interference, creating fading patterns. And you can see different fading patterns in the pictures at the bottom of the screen. And please note that WinProp considers all these effects. If we go slightly higher in frequencies, so for example, frequencies greater than 6 gigahertz, the penetration of building walls is hardly feasible because of the short wavelength. Therefore, line of sight or obstructed line of sight regions will dominate at these frequencies, meaning there is a stronger impact of the street grid on the radio propagation. Accordingly, the reflections are also therefore very important. But when it comes to diffractions, they are highly attenuated for higher frequencies and will more and more disappear if we go further higher, like millimeter wave frequencies. And the roughness for most of the walls will become large due to the short wavelength at these high frequencies like 6 gigahertz and above. So the diffuse scattering can be relevant, which is also considered in WinProp. However, um, scattering is considered, but it is difficult to use scattering for achieving a reliable connection, and it will be mostly through direct rays and reflections at these frequencies. Now, coming to the workflow in WinProp, there are different modules. For all the modules, ProMan or the propagation manager, that is the main simulation module. The other modules like wall manager or tunnel manager or antenna manager, those are all different supporting modules. How the general workflow will be in WinProp is in order to set up a project, whether it is for an indoor analysis or for an urban analysis, what you need is a database. Okay? Now, when I say database, if it is for indoor scenario, it's the building in which you want to do the analysis, the coverage analysis. If it is urban scenario or like a city, then the database is the map data in which we want to do this coverage analysis. Okay. So if you have the map data or the building geometry already available, you can import that into Wall Manager and make changes to it as needed, and make that database ready to be used in the propagation manager. Okay. And for the transmitters and receivers, you will need the antenna gain patterns. If you have the antenna gain patterns in any of the standard industry formats that will be supported in WinProp, they can be imported into ProMan and used as transmitters and receivers. If not, let's say you have just the 2D principal cut plane plots, then you can use the tool like Antenna Manager, where you can import those plots, trace on those plots to extract the data, and then generate a full 3D pattern from these two principal cut planes, and use that 3D pattern either as a transmitter or a receiver in ProMan. Let's elaborate a little bit more on the indoor scenario. For indoor scenario, when we talk about the wall manager, which is the database editor or builder, it's an extremely powerful tool. One can construct very detailed models of buildings or stadiums, which are typical indoor scenarios. You can draw walls within different thicknesses, add doors as subdivisions or windows with the different material properties, or even add furniture inside. Even if you want to add human phantoms to take into account the movement of people inside the building, you can do that. In fact, time variant scenarios are supported in WinProp, so you can select objects like human phantoms and specify the trajectory in which they will be moving and specify the speed with which they will be moving. All that will be taken into account. And WinProp comes with a huge library of commonly used construction materials, because when you're defining or creating a database, you need to assign the materials, and this library is of frequency dependent materials. You can even add your own materials to the library and reuse them in your projects. And instead of building a database from scratch, you can even import some existing CAD designs in many different formats. Or if you just have the floor plans of the buildings, you can even import those floor plans and start drawing on top of those floor plans to create the complete database in which you want to do the coverage analysis. Now that we learned about indoor scenario somewhat, let me demonstrate more in detail using a live example. So when you install the FECO software, there you will see a FECO launcher. The single installation file will install both FECO and WinProp, and these are all the different modules of WinProp: propagation manager, wall manager, antenna manager. There is a tunnel manager, and there is also a component manager. We'll start with the wall manager. So here you have the option to start a new database. So when you start a new database, this is where you'll have the option to say whether it is going to be an indoor database or an urban database, and whether you want to draw manually from scratch or draw with something like a bitmap in the background, or whether you want to import different CAD files and make changes to those CAD files. Okay. For example, if I select draw manually and click OK, then you have the option to assign some default materials in the beginning. Of course, you can always edit those material properties and reassign other properties if you want to change the material properties for any of the walls or subdivisions. So you will have the three principal cut planes in which you will be drawing your geometry, and you can see the full 3D image of whatever you're drawing in the 3D view. For example, if I select this add polygonal objects with orthogonal walls and ceiling, and if I like draw something in this 2D plane to create some kind of a shape. Now in the 3D view, you can see the outline of that geometry that I just drew. If I go into the settings, and if I say fill objects, assign colors to these objects, then you can see the complete solid object. If I want to edit any of these properties, what you can do is you can right click in these 2D cut planes, and you have the option to go to material properties to change the materials, or if you want to move the selected objects to a different location, you can do that. If you want to create multiple copies to create like a multi-story building to place one on top of the other, so you have all those different options. Okay. So what I will do here is I will try to open an indoor database that I created previously. So this is the database of an office building. So you can see the walls with the different colors depending on that material, and the subdivisions like doors inside those walls again with a different color based on the material properties. And the cut planes, if I right click and access the properties, I have the option to edit any of the corner coordinates to change the dimensions of that part, or even to change the material properties of that wall to something else. Okay. In the 3D view, you can also see like this has a floor. So just for the demonstration, the roof part is not added. But if I want to use this particular database and create an indoor coverage project, what we can do is we can open the propagation manager. And here, when you start a new project in the propagation manager, you have the option to select the scenario in which you want to do either the propagation analysis just for the wireless coverage, or if you want to go a step further and do the network analysis. Okay? When you do the network analysis, that is when you need to input the air interface model, which has the specifications of the technology, and accordingly you will get all the other output parameters like data rates and throughputs, reference signal output, SNIR levels, all that. If it is purely a propagation analysis, what you can get as an output is like received power at different locations, or the field levels at different locations, the path loss. So that kind of information is available from the propagation analysis. So if I change it from propagation to network planning, that is when it will ask for the wireless standards file. And if we select that wireless standards file and also import, okay, I think I selected urban. I will change it to indoor. So this way I can select the indoor database, which is the .idb file. If you have additional components for the transmitter and receiver, you can. If you use the component manager to define those, you can import them as well. That's optional. I click OK. And when you're displaying a cross-sectional view, so this is the height of that cross-sectional view. And you can see that database in the propagation manager. If I change it to the 3D view, we can again see the full 3D view of that office building. I go into settings and say draw horizontal walls. Then you can see the floor also. To set up a project, you must be in this 2D cross-sectional view. And when you are in the 2D cross-sectional view, that is when you can access these project parameters, where you can see the technology that you're trying to do the network analysis for. So all this data that it came into the project through that air interface model that we loaded. Yeah, you can see all the different transmission modes, the kind of duplex separation, if it is using MIMO or not, and all the different carriers that are used. Yeah. And if you go to the propagation tab, you can see the different outputs that are available as part of a propagation analysis. And under the network tab, you can see all the different results that are available as part of a network analysis. And going into the computation tab, this is where you can see all the different propagation models that are available within WinProp for the indoor analysis. If you want to do a full 3D ray tracing, you can look at all the different ray interactions. So you can use one of these ray tracing or ray optical propagation models. But if you're looking for speed, not compromising on the accuracy, then I would recommend using the dominant path model. So this is an Altair proprietary propagation model. By requirement, if you are to use any of the empirical models, there are also some empirical models available. Okay. So that is an overview of the different propagation models available for the indoor scenario. I, in fact, have the complete project with the results. So let me open that. So here we have a site with the 2 transmitters. I go and open the edit project parameters and go to the sites. To define the transmitters, the requirement is you need to first add a site, and within that site you can add multiple antennas. And because this particular technology supports MIMO, and we are using two MIMO streams when we are adding the transmitters. Accidentally close the project. Let me open it again. Yeah. So because we are using two MIMO streams, when we add a site within the site, we need to add two antennas for the two streams. And when I open any of the antenna, and if I look at the carrier, you can see the carrier that is assigned the transmitter power that is used and which MIMO stream it is carrying out of the two streams. So this is the antenna 1. If I open the antenna 2, again you can see so the frequency of the carrier. So if I click on assign carrier, so here is where you can see all the available carriers and you can select which one you want to use. So once you have the site with the desired transmitter, then you can request for the results. The results can be requested either in a rectangular plane or along a trajectory or at any specific points. Okay. Here, everything in this inside this red rectangle, that is our prediction plane. So there we will see the results. So if I expand the results from the propagation analysis, we can look into the power. But from the network analysis, this is where we can look into the additional data like the data rates. So if I select any of these pixels, you can see we have two MIMO streams and what is the contribution of each of these streams. And if I change this to throughput, once again, if I select any of the receiver pixels, then you can see the contribution of the two MIMO streams, which transmission mode is serving that particular receiver location. This way, by using WinProp, you can do the propagation analysis or the wireless coverage analysis to look at the received power, or do a pure wireless network analysis to look into the data rates and throughputs or the other output quantities like reference signals, RP or RSSI. Those are different outputs depending on which technology you are using for the network analysis. So that is on the indoor analysis. Coming onto the urban scenarios. For urban scenarios or scenarios on a city level, the wall manager can import and edit map data, which is typically a 2.5D building vector data. For indoor, we say it's a full 3D vector data because it can be detailed. Every wall can have different properties, different thicknesses. There can be subdivisions. So it's a very detailed scenario. But the urban one is 2.5D because each building is considered to be a uniform polygon. Okay? So there won't be additional subdivisions inside the building. Okay? That means on a city, different buildings can have different material properties, but one given building will have the same material properties for the entire building. Okay? That's why it's called 2.5D vector data. Okay? And if needed, you can also include vegetation to consider the effect of parks and trees in the city. Or if you want to consider the elevation of the ground along with the map data, you need to add the topography data also. Okay. If you look at the picture here on the right, that shows the example of an urban coverage analysis in New York with more than like 15,000 buildings. Okay. So the size of the scenario is not a problem for WinProp. It can handle extremely large scenarios easily. Let's look into And an example for the urban scenario as well. Let me open an urban project. So this is a city where we have these transmitters. If I change this to 3D view, now you can see the complete 3D map, different buildings with the different shapes and different heights. If I open the wall manager and load that map, so inside the wall manager, it's very easy to modify the shape of any buildings. Okay? So if I select one building in the 2D view, so you can see that is highlighted in the 3D view. To modify the shape, all I need to do is simply like select a corner and drag it, and you can see the shape being modified automatically in the 3D view. Okay? So if I right click and look at the properties, you can see the height. And if I change the height to, let's say, 100 meters, you can see all the other heights are automatically changed. And if I click OK, so you can see the height of the building changed. So this way, it's very easy to edit the map data using the wall manager. So once you have the final map, you will load that into ProMan, which is the propagation manager, to set up either the coverage or the network analysis in the city. Okay, so here there are several transmitters within this city, and if I look at the project parameters, this is again LTE technology, and you can see all the different carriers, the transmission mode supported. For this particular scenario, we are not doing any MIMO analysis, so we changed it to no MIMO, but you can see the duplex separation, all that. Okay, all the results from the network analysis and the propagation analysis. But moving on to the computation tab, these are the different propagation models available for the urban scenarios. Okay. Some of the models are similar to the indoor, like the dominant path model is available for the urban also, and the intelligent ray tracing is available for the urban as well. But the other models like standard ray tracing and shooting and bouncing rays, those are not available for the urban scenarios. Okay. There are some empirical models as well. So if by requirement you need to use, let's say, for example, the ITU propagation model, you can. Okay. In terms of results, once again, like with propagation analysis, you can definitely look at the received power. But if you want to look at the received power from all the transmitters, you can get that from the network analysis. And if you want to look at the data rates and throughputs, so this is the maximum achievable throughput in downlink as well as uplink. And you can look at the SNIR levels as well. If you select any particular pixel, you can see the contribution from all these different transmitter locations. So that's the urban analysis in WinProp. Moving on further, not only the indoor and urban analysis, it is also possible to do a combined heterogeneous network analysis in WinProp, meaning you can have an urban scenario where all the buildings are considered to be uniform polygons. But within that urban scenario, you can select one of the buildings and replace it with its indoor equivalent, with all the details, the subdivisions and the different details inside the building and all that. Okay, so this will help to do like indoor to outdoor or outdoor to indoor coverage analysis in WinProp. Okay. Typically, this capability can be used to understand the interference from indoor cells to the surrounding cellular network, or to know if the indoor repeaters are required for better coverage inside the buildings. Another scenario that is supported in WinProp is the rural scenario, and these scenarios are typically described by the topographical pixel data, where WinProp can handle both metrical as well as geodetic coordinates. Rural scenarios in general are much larger than the urban scenarios. The picture in the slide shows the field strength prediction in a large topographical scenario, where you can nicely see the shadowing due to the terrain profile. We have the transmitter on the far left corner, and on the far right corner you can see the shadowing effects. And optionally, if you want to include the clutter data, which defines the land usage that can be considered in the rural scenario, and it includes the properties like clutter height, clearance, as well as the frequency depending attenuation and ground properties. Because of the availability of WinProp, rural scenario in WinProp, WinProp is not only used for communication link predictions on Earth, but for that matter on any terrain, provided you have the topographical data of the terrain. Okay. This is an example of NASA using WinProp for predicting the communication link between the rover and the helicopter on Mars using the parabolic equation method in WinProp. So this PE method is available under the rural scenarios in WinProp. And this is a real mission, and they have the known measure data and validated the WinProp predictions with the measure data. And after the validations, once they gained confidence in WinProp simulations, they relied on WinProp to estimate how far they can navigate the helicopter away from the rover without losing the communication link. This is just to put everything together, a summary of different propagation models available under different scenarios in WinProp, along with the required databases needed to set up each scenario. Now that we have an understanding of WinProp capabilities, let's come back to that interference and coexistence issue. And we will try to explain that through a case study of interference between Bluetooth and Wi-Fi inside a residential building. We'll go through this in a step-by-step process. We'll first look at the house model that is used for the analysis. Then the Bluetooth device used in the study, which is a wireless Bluetooth speaker, as well as the Wi-Fi router that is also used for the analysis. Then we will go through the network analysis inside the building. We'll first cover the Wi-Fi network analysis, followed by the Bluetooth network analysis inside the same building. And finally, we will look into the interference issue between this Bluetooth and Wi-Fi. So let's start with the house model first. So this is the house model that is used for both the Wi-Fi and Bluetooth coverage. And this is a multi-story building. So you can see in this wireframe view, even the staircases inside the building. You can see depending on the material properties assigned to different parts of the building, they are displayed in different colors. So it's a very detailed building with the floor, walls, subdivisions, all everything specified in it. And here is a cross-sectional view showing what is inside the house. We have the Wi-Fi router in the corner of a room, and the Bluetooth speaker in the corner of the living room. Next comes the Bluetooth and the Wi-Fi devices. The first is the Bluetooth speaker. So here you can see a detailed model of the speaker with its dimensions. And here we have the acoustic port, a fan for cooling, the heat exchanger, as well as the PCB. For the PCB, you don't see the individual layers and the routing, but we can clearly see the Bluetooth IC and the main underline antenna that is attached to that IC. And these are the results from the electromagnetic analysis in FECO. We can see that the speaker shows excellent impedance characteristics within the Bluetooth frequency band. And you can also see the 3D radiation pattern of the antenna integrated into the speaker. This is at the 2442 megahertz, which is the Bluetooth operating frequency. Next is the router. You can see the two monopoles on the router. You will consider a 2x2 MIMO scenario. That's why we have these two antennas. So this will be for the 2.4 gigahertz band. And if you look at these results, the design works really well within the 2.4 gigahertz band. And you can also see that the two antennas have good isolation between them, which is required for MIMO. In fact, isolation in itself is not an accurate representation of how independently the antennas work. For that, we need to look into the ECC, or the envelope correlation coefficient. Yeah. When you look at that value, anything less than 0.3 is considered good, and our value is extremely low. That means we have a pretty good ECC for our Wi-Fi router. So we can definitely use this for MIMO. And these are the radiation patterns. So we can see the radiation pattern for each of the antennas at the 2412 megahertz, which is the carrier frequency that we are going to use in the Wi-Fi network analysis. We will also do the Wi-Fi network analysis for the 5 gigahertz frequency band. And at that frequency, we will use a 4x4 MIMO scenario. So that is why we have the router with the 4 antennas. And once again, you can see the antennas working pretty well within the 5 gigahertz Wi-Fi frequency band. And there is also good isolation between these antennas and the individual radiation patterns of all the 4 antennas. Next is the wireless coverage and network analysis inside that house. So if you recall the evolution of Wi-Fi technologies that we looked in the beginning, there were several Wi-Fi technologies standardized under the 802.11 series, and WinProp supports all of them. So let's compare two different ones inside the same house. So we will start with 802.11n, which is Wi-Fi 4, and then we will do the analysis for Wi-Fi 6 as well. Yeah. For Wi-Fi 4, we will consider 2x2 MIMO scenario and increase it to a 4x4 MIMO scenario for the Wi-Fi 6. First, we'll look into the 802.11n, which is the Wi-Fi 4. And the carrier frequency chosen for the analysis is 2412 megahertz. And you can see all the different transmission modes that are supported under this technology. And based on some online reference, the AARP power limit for this FDM modulation should be 20 dBm. And because we have two transmitters, we will use 17 dBm for each, okay, half of 20. The general workflow for network analysis will be we need to first do the propagation analysis, which computes the path loss and gives the received power levels at different locations. This is followed by the network analysis, which uses the path loss information and computes the network parameters based on the multiple access techniques, the duplex separation, as well as the transmission modes within that air interface model. Okay. So here, for our residential building, you can see the plot of the received power with an omni transmitter at the access point, which is the location of the router. Okay. Because it is better to visualize the results in a 2D plane. Now from here on, I'll try to plot all the results on a 2D plane rather than trying to show any of these 3D cut planes. We have already seen this router design. We are considering a 2x2 MIMO for Wi-Fi 4. So we will use both the antenna patterns as one for each of the MIMO streams. These are the network analysis results. The maximum achievable data rate is 92.8 megabits per second. When you select any prediction point, you can see the contribution from each MIMO stream as you saw in the live demo. The maximum achievable throughput in this case will be the same as the maximum achievable data rate because Wi-Fi 4 is an OFDM technology using time division or duplex separation. But if you notice here, the two MIMO streams are not adding up to the data rate or throughput at the given prediction point. Okay? Well, let me explain why. It is because of the fact that in WinProp, we just don't simply double the throughput when you're doubling the number of MIMO streams. We also consider the signaling overhead due to MIMO as well as the interference between the MIMO streams due to non-ideal separation. So this is exactly what will happen in a practical or real life scenario, and that is what we are trying to incorporate in the WinProp simulations as well. For the interference between the MIMO streams, you can convert the ECC to the interference ratio and consider that in the analysis. Moving on to Wi-Fi 6 network analysis. As Wi-Fi 6 supports the 5 gigahertz channels, we did the network analysis for that 5 gigahertz channel, and we selected the channel 106, which is 5.53 gigahertz. Okay. In general, Wi-Fi 6 supports up to 8x8 MIMO, but for our analysis, we considered only a 4x4 MIMO scenario. And when it comes to the power levels, once again, relying on some online sources, we made sure the power limit does not exceed 24 dBm. These are the individual radiation patterns which we already saw previously. So that is what we are using for each of the MIMO streams. For the Wi-Fi 6, with the combination of much higher data rate supported within that standard, as well as using a 4x4 MIMO with 4 data streams, the throughput is much higher than what we saw for the Wi-Fi 4, which is 802.11n. However, if you see, we don't have the coverage for the entire house because of the 5 gigahertz frequency band. So at this higher frequency, the wavelength is shorter and the signal is being attenuated heavily due to the penetration through the walls compared to the 2.4 gigahertz signal. So in general, you can say that the 2.4 gigahertz channels are for broader coverage, whereas the 5 gigahertz are for higher speeds. And one option to improve the coverage using the 5 gig channel would be using repeaters. And here you can see the throughput comparisons with and without the repeater. Use of repeater definitely improves the reception in large parts of the house, which is evident from the results. But of course, this will add or increase the cost. Another option would be to move the access point to a different location. In fact, it is also possible to do an optimization of the access point location for the optimal location inside the house. That is also supported in WinProp. So this is the comparison where you look at the coverage when you consider an alternate location for the access point. The new location slightly improved the results, but still you don't see the coverage in the entire house. So that's the Bluetooth and Wi-Fi coverage. Sorry, just the Wi-Fi coverage at two different technologies, Wi-Fi 4 and Wi-Fi 6. Now let's move on to the Bluetooth network analysis inside the same building. And for Bluetooth, 2442 megahertz is the carrier frequency. In this project, we did the network analysis for Bluetooth 5 technology. The 3 megabits per second EDR module is used since Bluetooth 2, but the other improvements in 5 are like an addition of 2 megabits per second high-speed mode, as well as the long-range modes. Okay. The output power is also increased from 10 dBm to 20 dBm when you look at Bluetooth 2 and Bluetooth 5. This is with an Omni transmitter, the maximum achievable data rate, which is 3 megabits per second. That means almost all of the house is being served with the enhanced data rate transmission mode. All the areas inside the house where the SNIR per bit or the EB by NO is greater than 7.8 dB, that is served with the enhanced data rate, which is once again the entire part of the house. That's why you see maximum coverage in the entire building. Of course, in the corners, there is some loss in the coverage. That should be okay. Now, if you look at the maximum achievable throughput of the Bluetooth, it's 19 megabits per second. Bluetooth being a pocket-based protocol with like a master-slave architecture, when one master can communicate with up to 7 slaves in a piconet. So for this CDMA-based technology, the maximum number of codes available for users on one carrier are set equal to the number of slaves, which is 7 in this case. In an ideal scenario where the codes are perfectly orthogonal to each other, the maximum achievable throughput would be 7 times maximum achievable data rate, which is 7 times 3, 21. However, in WinProp, we consider non-ideal scenarios with an orthogonality of 0.8 instead of 1. That is why the throughput is only 19 megabits per second instead of 21. So this is the Bluetooth model that we saw previously, the speaker. So instead of using the Omni transmitter, we'll try to replace that with this Bluetooth gain pattern. Now, if you look at the comparisons between the Omni as well as the Bluetooth speaker, you can see they are pretty similar to each other. This means our Bluetooth antenna pattern was like a near Omni pattern. Now, when we subtract one result from the other, just to look at the difference between having an Omni versus replacing it with the Bluetooth speaker pattern, you can see the difference is almost zero for a major portion of the prediction plane. Now that we looked into both the Wi-Fi and Bluetooth network analysis, finally, let's move on to the interference between these two technologies. In WinProp, it is possible to consider the interference from one technology in the network analysis of another technology. And this can be done by importing the coverage results of one as an interfering source in another. Here, we will be importing the Wi-Fi as an interfering source in the Bluetooth project. The interferer can be radiating on the same carrier frequency or a different carrier frequency. So you can select that option. You also have the option to consider some additional attenuation of the interfering signal. This is typically set to the attenuation level of a filter used to mitigate the interference. So this way, we can also study the effect of filters, how much attenuation we need from filter, which will help in deciding or selecting a filter. Let's see how the 2.4 gigahertz Wi-Fi is affecting the Bluetooth throughput. If we recall from the plot of Bluetooth, the entire house was served with maximum achievable throughput. But here we can clearly see that the interference from Wi-Fi is severely affecting the throughput in the areas closer to the router. And here you can see the Bluetooth throughput when the interference from the Wi-Fi is attenuated with a better filter. So instead of 20 dB, we specified an attenuation of 40 dB. Yeah. We can clearly see the throughput can certainly be improved with a good filter. So far, this is all with the 2.4 gigahertz Wi-Fi interfering with the 2.4 gigahertz Bluetooth. Let's see what happens if we use the 5 gigahertz Wi-Fi channel interfering with the Bluetooth. The 5 gig Wi-Fi signal being in a completely far away frequency band from the 2.4 Bluetooth, and also not even a harmonic. There is not much of an interference between these two. So that's why you see the coverage is not being impacted severely. So from this study, we learned that the interference analysis will help to identify the affected areas and the amount of filtering needed to improve the coverage. Okay? So this will definitely help in designing or selecting a filter to mitigate that interference. Before closing out, let me quickly go over some of the useful resources provided by Altair for students. Of course, everyone likes free software. I would like to highlight that the fully featured FECO and WinProp software are available to all the students for free. So please do take advantage of it. Along with free software, there are several e-learning modules available on the Altair Learning Center, both for FECO and WinProp. And help is also available through the community forum. So if you run into any issues while exploring the software or when working on a project, please search the forum for solutions. If your issue is not already addressed, please post your questions. This forum is not only for all the different users to answer, but is also monitored by Altair employees. So if you don't receive answers from other users, one of the Altair employees will eventually reply to you to resolve the issue. But this community is also a great place to interact with other users and engage in some technical discussions. That concludes the webinar. Thank you all for joining today.